we shall prove the second theorem of welfare economics. Let us see our assumption. First is well known. For every consumer H, the consumption set is equal to the non-negative object. This is only to simplify the proof. Then, preference relation is continuous locally non-saturated and convex. This is an acronym for locally non-saturated. 1 over for every bundle XH divided XH, the inclusion VOH of X of H, pH of XH, sorry, is a subset of a positive ordinate. Positive. Huh? This means if you have any bundle like this, set of preferred elements do not touch the horizontal vertical axis. This means, from an economic point of view, that every good is indispensable. Without a positive quantity of some good, you are in the lowest possible level of satisfaction of your needs. For example, if every preference relation can be represented by a Cobb-Douglas utility function, this result is assured, but generally speaking, our preference relations are not regular, and therefore they are not necessarily representable by means of utility functions. However, if all these set of properties is verified, then for every Pareto optimum, weak Pareto optimum, like these, there exists a price system, a non-null price system. And that tells at least one element of this P must be non-null, such that for every x prime h in pH of xh, p times x prime h is greater than p times xh. What is the meaning? Take any weak Pareto optimum. There must exist a price system such that, note, every bundle which is preferred for every side to XH must have a greater value than xh. Right? In other terms, the idea is the following. Redistribute the total endowments in a way such that each subject receives exactly this bundle. The bundle included in the weak Pareto optimum. Well, according to this price, note that every bundle which is preferred to the initial endowment is too expensive, is outside the budget constraint. What is the conclusion? With this price system, no subject has convenience to exchange. Right? Because you are in a Pareto optimum. Right? Suppose this is the initial point which represents initial endowments. This is a Pareto optimum. Substantially, if you modify initial endowments so that the new point which represents initial endowments is x itself, clearly with this price system, no subject has convenience to exchange goods with other subjects. And so we are in an equilibrium. In a very particular case of equilibrium, of course, without exchanges, but however, it is an equilibrium. Is it clear? This is our theorem. The first theorem of welfare, the second theorem of welfare economics for a pure exchange economy, of course. Now, first step. Consider these points, x1 for the first subject, x2, etc., xh. And consider the set of all preferred elements of this point. The first step consists in summing these sets. What is the meaning to sum of sets? It's really a very simple method. Suppose that there are only two goods and only two households. The consumption set of each household is exactly equal to the non-negative order. The set. And suppose that the bundle of the first subject is these, while the bundle of the second subject is these. This is the set of preferred elements of the first subject, and this is the set of preferred elements of the second subject. There, I have superimposed with the same graphic the preferences of both the first and the second subject. Now, compute the sum of these two sets. What is the meaning of this concept? See, it is simple. Take any point which is preferred to x1, say x prime 1, and any point which is preferred to x2, say x prime 2. Then sum them. You remember, the sum of two vectors is nothing but x prime 1 plus x prime 2. Simply by summing component by component these two vectors, you obtain the sum of the vectors. From a geometrical point of view, you must apply the well-known rule. The point is prime 1 plus x prime 2 is the opposite vertex of this quadrant. Huh? Well, I made the sum of these two vectors by choosing x prime 1 and x prime 2 in these two sets. Repeat the same procedure for every pair of vectors in these two sets. For example, take also this point and this point. Sum them and obtain another point, etc., etc., etc. Right? By putting together all these points, we obtain this set. The set is the sum of the different sets, pH of xh. In this case, there are only two consumers, but the procedure can be repeated for any number of goods and any number of households. Denote by A this set. Large A is the sum of this set, which is obtained by means of this procedure. Is it clear? I repeat. First step of the proof. It is necessary to sum these sets. But you are not accustomed to the concept of the sum of sets. However, you are accustomed to the concept of the sum of vectors. But by the second, it's possible to define the first concept of the sum. In other terms, take any elements in the set of preferred elements to x1 and any element in the set of those preferred to x2. And sum them according to the usual quadrangular rule, you obtain this vector. Complement by complement, you are summing these two vectors, or generally speaking, h vectors. Repeat this procedure for every pair of points, one in this set and one in this set. You obtain a larger set like this, which we shall denote by large A. This is a well-known geometrical procedure. You obtain this set. Clearly, since both P1 of x1, P2 of x2, generally speaking, pH of xh, are convex set, also this is a convex set. And moreover, since by local non-saturation all these sets are non-empty, also A is non-empty. So is a non-empty convex set. Is it clear? Well, this is the first step in the proof of the second theorem. Now, the fundamental result. Does redraw this setting. Suppose that by sum our sets we obtain this setting. Now consider the point sum range changes from 1 to large h of the vectors xh. This is the sum of the vectors which are in the Pareto optimum. Where is with respect to A? It is easy to show that this vector cannot belong to A. Cannot belong to A. In reality, it is on the boundary of A. Because this tuple is a weak Pareto optimum. Because suppose I'm assuming that this sum is an element of A. By the definition of a set A, which is the sum of these sets of preferred elements, there would be x prime 1 which belongs to P1 of x1, etc. X prime h which belongs to pH of xh, such that sum of these x prime h is exactly equal to the sum of xh, by definition. Because if this point where an element of A, since A is the sum of elements of the preferred sets of the vectors in the Pareto optimum, it is assured the existence of x prime 1 and x prime h, each of them is referring to x1, etc., xh. Such that this equality holds. It is necessary, by definition. But is it possible? No, because this actuable was a weak Pareto optimum. Here you would have a redistribution of resources which ameliorates the condition of every subject. Impossible. By definition of a weak Pareto optimum. Therefore, this point does not belong to A. By local non-saturation, however, this point is on the bound of A. Is it clear? I repeat the second part of the proof. After defining this set A, the sum of those sets we introduced a moment ago, let us consider the following problem. But the total consumption vector is an element of A or not? And the answer is not an element. Because this actuable is a weak Pareto optimum. In effect, if this vector were an element of A, since every element of A can be expressed by the sum of elements which are preferred to example 2, etc., 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 and there would exist x prime 1 in P1 of x1, etc., x prime h and pH of xh, such that the sum of these alternative bundles is exactly equal to the sum of vxh. But this is impossible, because this would mean that it is possible, by redistributing the total resources of the economy, to ameliorate the condition of every subject. In contrast with the assumption according to which this equitable was a weak Pareto optimum. So, this point does not belong to the set A. Last step of the first part of the proof, where I shall cancel anything in order to prove the second part. The set A, by construction, is a non-empty convex set, but clearly also the set which contains only this vector is a non-empty convex set. Obviously, it has only one element, so it is non-empty, it is convex. But you have two convex sets, A and this singleton set. Which are separated because there are no elements in common. So it is possible to separate, they are disjoint. It is possible to separate this point from the set A. More precisely, where exists a P right system structure with at least one well-known component, such that for every x in A, P times x is greater or equal than P times sum of xh. Is it clear? You obtain this result. Separation between these two convex sets, H and this set which contains only the sum of xh. Since these are two convex sets which are disjoint, there exists a separated hyperplane between them. Separated hyperplane which verifies this condition. This is the exact point which the separating hyperplane theorem is applied. Is it clear? Now, here ends the first part of the theorem. Now we must prove the second part after a short interval.